Okay, thank you very much for coming to this presentation. What do you mean by cache-friendly? I'm Björn Fahller. I live in Stockholm. I'm quite active in the C++ Stockholm C++ community. So if you're in town, please get in touch. We can geek out with like-minded people, or maybe you can do a presentation at our meetup. Phil did last month. It was very popular. What more? Yeah, I work for Net Insight in Stockholm. We make networking equipment. We make everything from the mechanics and the electronics, the FPGAs, low-level software, the network communication stack, video services, network management system, the whole thing. And this talk is actually related to that. You see, we were making a new machine, and a bigger, faster, better. We had more CPUs, faster CPUs, more memory, more FPGAs, faster FPGAs, and we were getting towards the end of the development of this, and I wanted to run a performance stress to see how well does it perform. I wasn't worried about packet forwarding and such like, because that is handled by the FPGAs. They're good. So I did other kinds of stress. I set up a small network, added, changed, removed connections randomly, and messing with the network topology, like pulling fibers, rebooting machines back and forth, everything at the same time. And performance was not great. It was quite disappointing, actually. So I did what you do, try to find out where does the time go, what's happening, and I could see that the central node controller CPU was pegged at 100%. More specifically, the control daemon that is responsible for the communication and for routing, so network topology things, and it was pegged at 100% CPU. And this does not make sense. This should be limited by communication across the network and by communication to the other machines, these other computers on plug-in boards. It should be limited by latency. Why is it pegged at 100% CPU? So I ran a profiling on this daemon, and I saw that it spent about 75% of all its cycles in one function called schedule timer. What? Okay, so dive into the code. It looks like this. This is a simplification, but roughly like this. This is an old C API. So I have a timer callback, which is called with a void star. That's up to the person who registered the timer what the void star will mean. And we have a deadline in milliseconds, which is a point in time. This wraps, I don't know, every 15 days or whatever it is. We never have timers that are more than a couple of minutes in the future, so it's okay. And the callback and the user pointer, and then we have, you can see that this is a doubly linked list, an intrusive list. So we have a timer route called the timeouts and schedule timer here. When you call it, it iterates this list, start from the end and goes towards the proper insertion point and then adds it. And then cancel timer, because many timers are canceled. They are typically for example, sending a message across the network and you expect a response within some time, and almost always you get that response, so you cancel the timer. And if you don't get that response, you act on the timeout event. I guess some of you can see where this is maybe not performing very well, especially if I say that when I found this problem, when it spent 75% of all CPU cycles in schedule timer, it was hovering at a list length of roughly 20,000 timer events. This presentation, what do you mean by cache-friendly, is the presentation I wish I had attended a little more than 20 years ago, because the person who wrote that linked list is standing right here. And I can honestly say I did not have knowledge about what these things actually meant. In defense of younger me, at that time when I wrote that system, the system was much, much, much smaller. We had rarely more than a few tenths of events, and they were almost always equally far into the future. So you almost always just appended to the end of the list. So it worked well. And quite frankly, it worked well for more than 15 years before we found a problem with it. So it wasn't terrible, but it certainly didn't scale. So, to discuss this, I'm going to talk about something that is called being cache-oblivious softwares, cache-oblivious data structures or algorithms. This is a term I absolutely hate because it's not at all about being oblivious to the cache. It's quite the contrary, but it's about being oblivious to the specific details of the cache of the machine that you're running on. So my simplistic mental model, it works like this. I say that there is a cache and it's small. It's very small, tiny. And it consists of fixed size lines. I will get to that later, what we mean with that. And it's small, and it's fast. It's super fast. So when you do a memory access that hits the cache, it's fast. And when you miss a cache, because it's small, then it's slow. Then you have to go to main memory, and it's very small, very slow. But since this is a simplified mental model, it excludes something. For example, it excludes that pretty much every single CPU in existence today has multiple levels of cache. It's a hierarchy. So you typically have a small level 1 cache per core. Then you have maybe level 2 caches that perhaps are pairwise for cores, and then you have a level 3 cache that is shared by all CPU cores. It depends. This actually differs from CPU to CPU, but in this mental model, I actually don't care. I care that it's small. That's what I care about. I don't care about associativity. Associativity can, in some cases, be important. What we mean with associativity is that in an ideal cache, then any memory address in your main memory could be mapped to any position in the cache. And that is not the case. You are limited by which entries in the cache can be referenced by any memory address, which means that if you're unlucky with your access patterns, you can get something that makes your cache appear to be considerably smaller than it actually is. But I'm not going to go into that other than what I just said. I'm also not going to mention much about threading other than, as I mentioned with the cache hierarchies, you typically have a level 1 cache per CPU core. And when you have threading, if you communicate information across threads, you write, one thread writes to memory on its core, and another core must see that change, so it must transfer the information from the level 1 cache on one core to the level 1 cache on another core, and that is expensive, it costs. So avoid that as much as you can get away with. You can obviously not get away with it completely, because then you would just use separate programs. But reduce it as much as you possibly can. So, all models are wrong, including this one, but some are useful. I maintain that this one is useful. At least I have found it to be. So, here's my super advanced computer architecture. So, to the right, you see the main memory. It's huge. It has 16-bit address space. It's huge. And in the middle, we have a cache. It's tiny. And you can see now that, in this case, I have cache lines of 16 bytes. 16 consecutive bytes. And whenever you're communicating with memory, read or write memory, you're always reading or writing whole lines. You're never, ever writing a single byte into memory. And what happens here if we try to run this program? So I want to read from this pointer hot at 4004 hex. We can see that 4004 is in the cache on the second line from the bottom. So this is a super fast access. It's a cache hit with just boom, almost no time at all. But if I want to read from cold at 4048 hex, this is not in the cache. So what happens is that the cache picks some line and say, sorry, you're out. Evict an entry from the cache so that we can find the real address, read it into the cache. This is a slow operation, really slow. And then we can read it. And likewise, if I want to make a write to 4080, 4080 is not in the cache. So the cache will find something to evict. Let's say that this entry actually has some changes to it. There had been writes to this address that have not yet gone to main memory. So it cannot just throw this away because then the change has been lost. So it must write it to main memory, evict it, read the real information back in so that we can do an update. This is slow. And then we get the other 4 bytes up from here. And now it's actually not cold anymore. It's in hot cache, so this is super fast access. This is my mental model of a cache. It's super simple, but it's useful. It helps you reason about your computer's behavior, your program's behavior. And then sometime in the future, the cache line is written back to main memory so that it's not lost. So, in analyzing this, I wrote a program. I really don't want to call this a benchmark, because a benchmark is supposed to be a fair representation of real-world use, and this is not it. This is just something that I'm trying to explore. What are the memory access patterns, the cache access patterns of operations on this timer? So what I'm doing here is I have this loop over 20,000 times, and for every revolution I schedule a timer. And here is one of the tricky things with doing this, is that you need to do some work that is small enough that it doesn't contaminate your measurement by adding too much load. But you also don't want it to be so simple that the compiler can see that, you're not doing anything here. I can simplify this a lot. But in this case, it turned out to be sufficient to schedule a timer that does nothing. It was good enough. The compiler cannot see through this. And then every second time through this loop, I cancel the timer that was scheduled on the previous revolution in the loop. So that when we're done with this over 20,000 times, there are 10,000 entries remaining, and then we shoot them in order. All right? And the shoot first is just, if the list is empty, we return false. Otherwise, we shoot an event and return true, so we can go through it. So, first analysis tool, Valgrind. Are you familiar with Valgrind? So most people use this to catch memory errors like use after free or reading uninitialized memory. But Valgrind has other tools too. So Valgrind is one that I've used a lot. So Valgrind is essentially a profiler. The Valgrind tool itself is a CPU emulator. It analyzes the instructions and runs them in an emulated environment. Valgrind keeps track of, for every instruction, where in the call chain are you, and the time spent roughly. It's not cycle accurate, but ballpark. So that you can see where has your program been running, what's happening in it. And it also includes a cache simulator. So you can say that for every memory access you do in your program, do check if the access is a hit or a miss. But it simplifies it a little bit. It tries to emulate the cache on your hardware, but it squashes it to be just level 1 and the last level, and every level in between it ignores. But the cool thing is that it defaults to mimicking your cache, but you can actually say that, no, I want to run a test on this with a cache that is constituted in a completely different way. That can be useful sometimes. And then I say dump instructions, because normally CallGrind does the dump information per source code line. But I want to see per instruction what's happening. And I also want to see branch sim. Modern CPUs you have branch predictors, and you do speculative execution of code, and this branch sim will not be perfectly the same as your CPU, but it tries to mimic a branch predictor, so you can see where you have prediction misses. And it's slow. It's so slow. 20x slowdown is nothing unusual at all. But it's pretty cool. So let's actually have a look at this. So yeah, first thing, I'm running everything on this laptop, and it has a Ryzen 9 CPU. We can see that the level 1 data cache is 256 kilobytes per instance. Notice the kilobytes. K, small. You probably have strings that are longer. And we have another one for the instruction cache. I actually don't care about this one in this presentation. And the L3 cache is 16 megabytes. It's quite large. What we cannot see here is that the cache line sizes are 64 bytes. This is it seems to be the de facto standard on CPUs today. There are probably exceptions, but most CPUs seem to be 64 bytes. So here's another thing also. This is, I don't really feel good about this. I'm using 01, so it's not super optimized. The reason is I don't want to run it on unoptimized code, because unoptimized code is just stupid. It's bad. It's so bad code. 01 is good enough to remove the stupidities, but it's still not optimized so much that it's hard to follow. It's actually quite easy to follow the code at 01. If you go to 03, it can be really difficult to understand what on earth, what is happening here. What is the relationship between these instructions I see and the code that I have written? But 01 seems to work all right, and you get the same memory access patterns as you do on higher levels. That is my experience. Today, this may change. We'll see. By the way, feel free to interrupt with questions. I should have started this right away, because it's actually super duper slow. So, like I said, this is now, it's an emulator. It looks at each and every instruction, say what I should read from this memory access. That is not a hit in the L1 cache. It is a hit in the L3 cache, noted, thank you, and this was a call chain to it, and I estimate the time for this instruction to be that, and here we do a conditional branch. What does the branch predictor say? Was this a hit or was it a miss? And it does a lot of work, and it's not fast. And I don't know if can you on the front row hear the fans? It's very busy right now. Collecting statistics. So. Is there an option to start collecting from the middle of the run? Yes. That is also one of the cool things with the Valgrind, is that you can actually include a header. It says, so there are two things you can do. You can include a header, valgrind.h, and then you can embed instructions. What these instructions are assembly instructions that no compiler would ever emit because they are nonsense, they don't mean anything, but they mean something for this emulator. But there, you can also say, there are flags on the command line that you can say, start without collecting and begin collecting when you enter this function. You can do that. Okay, so we have some statistics here. We can see that we have 2.5 billion instructions, 1 billion data references, 720 million D1 misses. We have 70% of all memory accesses miss the L1 cache. That is impressively bad. And we can see that, yeah, branch miss predicts that that is not really a problem, and so on. But yeah, wow. So, but the cool thing is the analysis tools. So CacheGrind is a visualizer for data here. And you can see a lot of things. You can choose, this is too small for you to read, I won't spend too much time on it. But what I've selected here is, I want to see the sum of all L1 access misses. And we can see where in the program they are. And we can also see here a call graph, which in this tiny program doesn't really add information that you didn't know. But when you're analyzing a bigger program, it can really help you zoom in on where your problems are. But we can see that this loop to find the insertion point, that is the problem. So we have 2/3 of all cache misses are in the condition for the while loop, and 1/3 are in going backwards to the previous element. So we can look at machine code here. So I don't know if it's possible for you at all to read, but we read this memory address, and we check for, compare it with the value that we have in a register. And then we have a jump, conditional jump after, so it's a comparison on size. So from this, we can conclude that this is actually this condition, this is after. And the other one here is the assignment when going one step back towards the beginning of the list. So let's try to see, what does this actually mean then? We have our timer struct here. What can we make of this? So uint32t deadline, that is 4 bytes. And we have 4 bytes of padding because the callback is a pointer that must be on 8-byte alignment. And we have the user pointer, 8 bytes. And we have our next pointer and prev pointer. So I have a sum of 40 bytes. Remember when I said that when I was doing this check on the new product we had developed, and it was hovering at around 20,000 elements. 20,000 times 40 is a heck of a lot larger than the L1 cache. So on the average, an insertion blows the entire L1 cache. Yay. But we saw that 66%, 2/3 of all cache misses were on reading the deadline. This makes sense because we follow a pointer to, we have a pointer to some entry. We don't know where it is. It's probably a cache miss, which means that to read this deadline, it is a cache miss. We get that. And then we had, yeah, so rule of thumb, if you follow a pointer, assume it's a cache miss, unless you have really good information to the contrary. But we have 1/3 of all cache misses are on going to the previous element. Why is that? Any ideas? Sorry?
It's not aligned.
Yeah, exactly, alignment. So this prev starts at 32 bytes from the beginning of this struct. And if this happened to be aligned perfectly with the cache line, then it would be Then we would get a miss for the first reading the deadline, but we would get a hit on prev because it's already in place. But if, say, this timer, its address is halfway into a cache line, then we get a miss for reading that one, and then we get to prev, and that is just after the cache line. So we need to read that one from main memory too, so it's a second cache miss. So that is also a thing. Keep your memory small. Keep things you access near each other in time, so the temporal locality. Keep them close in memory too. So chasing pointers is expensive. Let's get rid of the pointers. This is fun. So rewrite. I have a different structure here where, to begin with, we've gotten rid of the pointer, so we have just 24 bytes per entry, so that it's good, it's smaller. And I'm storing everything in a vector, so it's a large, long, contiguous store. And when we schedule a timer, we start with making space for the new entry, and then we loop by just moving the elements further back until we find the insertion point. This is patently stupid. We're doing so much work here, absolutely crazy, but let's try it anyway. And then we find the insertion point and stick it in. And the cancel timer is similarly, we do a linear search for the timer ID. And the reason I need an ID here is that in the previous example with the linked list, then the elements never moved around. The pointer was the identity. Here the entries move around in this vector, so I need something to identify them with. That is the timer ID. So I do a find linear search for the entry that has the correct ID, and then we erase it. So let's look at some other tools. On Linux, that is what I'm used to. I'm sorry, I don't know other operating systems well enough to say much about them. Perf is a really good tool, perfstat especially. It presents statistics from the whole run of a program, but it uses hardware counters and the counters that exist in the kernel anyway. So hardware counters, there exist hardware counters for memory accesses, cache misses, cache hits, and things from the operating system are like when context switches and such things. And you can choose which of all these counters you want to have a look at. I like to look at the number of cycles spent and the number of instructions spent, because a modern CPU can execute several instructions per cycle. So if I see that I have many more instructions than I have cycles, then the CPU is pretty busy. If it's the other way around, then the CPU is waiting a lot. So that is a clue for what is happening. And I'm looking at the L1 data cache for when I have loads and misses. Yeah, speculative execution can make these a little bit confusing. I'll get back to that later. And this is amazingly fast. It's basically no overhead at all, because it's just getting a snapshot of the counters before you started running the program and taking them again when the program exits. So it's enormously fast. And then we have perf record. But before going into that, I should mention both AMD and Intel have really good tools for analyzing these things with fancy GUIs. I'm not familiar enough with them to feel comfortable presenting them in here, but take a photo of these links and have a look at them. They're really good. I don't know if there are similar tools for, say, ARM or I don't know, PowerPC. I don't know. But these are good tools. But back to perf. Perf record it's working statistically. It's polling frequently. It's doing this. Get all the counters. And this means that you get a statistic view of where does your program spend its time? Where do the counters move? Where do they increment? So So for an extremely short run, you can get very confusing results. For a long run, you get very good results. Because after all, if you are sampling randomly, you are likely to hit the hotspots because that is where you spend most of the time. So the thing I'm adding here is that I wanted to store call graph information, because if you don't, then you just see where in the code are you, but you don't see how did I get there, because a function may be slow when it's called from one path and fast when called from another path. You need, do I need a particular linker option for the call graph? You need debug information. That is what you need. No, you need debug information. I should mention that on Intel CPUs, you can use another flag, this kind of call graph equals, I think it's LBR, that uses some Intel internal register that works even without debug info. And it's actually faster too. But I'm on an AMD Ryzen and it doesn't have support for that. And it's fast. It's not as fast as perfstat, but it's fast. It's really fast. So let's have a look. So I have our linear array program here. You recognize this schedule timer with this loop for insertion, cancel timer, shoot first, and this driver to see what is happening in the system. So actually, let's start with the linked list, but just to compare. So you remember how long time it took when I ran it through Valgrind, and this is a little bit faster, a tiny little bit faster. So linear array, boom. Okay, so a lot fewer cycles, a lot more instructions, a lot more memory accesses. Interesting, but fewer cache misses. What's happening here? This is curious. So let's record this so we can see where the time is spent. One really cool tool for Linux is Hotspot. I'm sorry you're not able to read this, so I'm not going to go into much detail, but one cool thing that you can do is to get the flame graphs and you can see which functions have you had the costs in, and you can look at the old, these are for cycles. I want to look at where we have the dcache load misses. Mem move, mem copy, interesting, yeah. This is a really good tool for when you have a bigger program to zoom in on which function and which path to that function is your problem at. Unfortunately, it doesn't give you any way of seeing, that I know of anyway, of zooming into a function and analyzing which instructions are causing the costs. But you have a terrible tool for that instead. Perf report. Oh, great. I hope the lost chunks doesn't ruin the presentation. Let's see. So I'm going into the cache misses. So we can see to the left, you have how much time is spent totally in a function, including all the functions it calls. And then you have this second column, self, that is how much of these events, in this case, load misses, is spent in this function alone, regardless of what it calls. So we can see that we have a lot in memmove. We have a lot in schedule timer and cancel timer. Let's look at schedule timer. So we can see here, here is where things get a little bit weird with this sampling, the periodic sampling statistical information that you get, because it says that we have 28% cache misses in this jump instruction that doesn't touch memory. Go figure. But it's, so you have to read these with a little bit of reasoning and say, well, how can this be? Well, it's probably because it gets its value from reading this, from this comparison that comes from reading this memory, probably. So we can probably clump these two together and say that these are one problem area. And likewise here. So it's maybe not so strange that we get cache misses when we move entries towards the back to find the insertion point. So, I asked this on Twitter some time ago, and I think Miro Knape really nailed this with what surprised you the most when learning about CPU cache, that doing more work can be faster than doing less. And this was doing so much more work, and it's a lot faster. So, yeah, let's cache it for you. So, we still see that linear search is expensive. Is it worth doing a binary search? Let's try it. It's, the structure is actually exactly the same because we already had the vectors sorted. We have them in timeout order. So we can just change schedule timer to use lower bound to do a binary search to find the insertion point and then do the insert. Which means that it should be far fewer memory accesses to find where to insert, and then you just move one huge block of memory away. And cancel timer is similar. I use equal range here because we can have several timers with the same timeout time. So I use equal range to find when the timeout time is, and then in that range I do a linear search for the timer ID. And then we can erase the entry. So let's have a look at this one. So same thing, schedule timer with lower bound and cancel timer with equal range. Let's do this one first, just so we have a comparison. Okay, so nearly twice as fast. That is interesting. Way fewer cycles, way fewer instructions. So we see that the efficiency of the CPU is sort of down. It's waiting, but there are fewer memory accesses, so maybe it's okay. Fewer cache loads, not so many fewer cache load misses, some. Branch misses are up a lot. Oh. Why is that? Any ideas? Yeah. Yeah, so it's, when you're doing a binary search, the CPU is trying to find a pattern. Is it true or is it false? And it's completely random. It doesn't stand a chance. I will do a detour here, because this is something I cannot show on this machine. The first time I did this, I ran it on a CPU that was an Intel CPU, 5 years old now, roughly 6 maybe. And I got an extremely confusing result. Because what this showed me, perf_stat, it showed that the L1D cache load misses were 102%. And like, go home, Linux, you're drunk. What happened is that does anyone have a guess? Speculative execution, yeah. So what happened on this 5-6 years old Intel CPU is that when it comes to a branch instruction, it guesses where to go, and it starts executing the branch that it guessed. And if it turned out it's not true, then it have to go back and continue again. That is still true. But what happened then was that if something that was executed in this branch that was executed by mistake did a memory access, and that was a cache miss, it evicted something from the cache, did the read to get the correct memory, and then it threw the result away. But it still counted as a cache miss. And this, dear friends, is Spectre. That was popular a few years ago, the vulnerability about caches and speculative execution. So I accidentally discovered Spectre. Unfortunately, it was already discovered, so I cannot claim anything. But I was really confused. But I got a better appreciation for what that vulnerability was about. So if you're running things on a CPU that is a few years old, you may run into this, and now you at least know why you get really confusing results. So the searches, actually, I went a little bit too fast there. I should definitely do a record so we can analyze this. Where do I have the load misses? Memu, yeah, we knew that. And yeah, that's pretty much that. Yeah, it's Memu. Okay. Yeah, 1.86%. That is a rounding error. It's nothing. So yeah, Memu. This program does Memu. That is what it does. So the searches are basically not there. The binary search, even though I'm actually looking at where I have the cache misses. But the number of cache misses are high, and as we saw, memmove dominates, so the next logical step is, of course, to write a faster memmove, right? No, our job is not to write a faster memmove, it's to move less data. So, let's do a comparison. So this is interesting. So what this graph is I can show what I've done. I've taken just this inner loop and shoot timers. That is what I'm calling a large number of times. And the time is then divided by this number, and I'm changing this number. So that is the x-axis. How large is this number? So if it would scale linearly, then I would just have a flat line, because then every insertion, every removal would take exactly the same time. So what we see here is up until about 500 elements, the linear search is faster, roughly speaking. After that, we get a small gain for the binary search. That is worth keeping in mind. I couldn't show this, but I mentioned that you can get really, really, really weird results on a few years old CPUs. Should we try a map there? It's popular to hate map. It's in the, who's in the map hate club? A few hands, not too many. Okay, the rest of you are shy. The reason for trying a map is that we saw that the binary search pretty much itself disappeared and memmove dominated. So yeah, map means chasing memory, but since the elements are stable in their position in memory, we will not need to do memmove. So yeah, we will get cache misses for pointer chasing, but is it worth it or not? It's maybe. Simplest implementation of them all. Schedule timer is just do an insert into a multi-map. Cancel timer is just erase, because the timer type is just the iterator into it. Shoot first does a little bit more work, because we have to find the beginning of it and call it, etc. But so let's have a look. So here's the implementation using the multi-map, insert, erase, shoot first, the same loop. For comparison and map, what do you think? Good, bad? You think it's worse? Okay, let's have a look. So the first thing about profiling is that you're wrong. You're always wrong. Your intuition is wrong. I did not expect this to be fast either. So actually, this is so fast that it's not meaningful to get this result. So let's get a longer run. So now we cannot really compare the results anymore, because we're doing 100 times more work. So we cannot compare with the previous ones. But we can analyze it at least and see where is the time spent. But my mind is gone now. So report, yes. It has a bit more work to do. So where do we have our load misses? Something, RB3, whatever, I don't know. Insert and rebalance. Rebalance for erase. But what is going on here? Let's have a look at this one. Reading standard library code, lovely, lovely. What's happening here? So we have a loop, checking if it's not 0, that is this test, I guess. We do a key compare, so we read from offset 20 into a node, and then compare and branch if it's before. Okay, so this is finding the element to look for. It must be. So at offset 20 is the key. Yeah, that is what must be happening. Let's not dive deeper into how studmap works. So, Mathieu, I'm sorry. Big O actually matters. It really does. But actually, in Mathieu's defense, when I studied computer science, then the breakpoint for when it mattered to do good algorithms, low algorithmic complexity was like 5 elements. It's a lot higher now, because CPUs today are working in completely different ways. When I studied computer science, every memory access was equal. This is not not the case anymore. So it is faster, but we have a lot of cache misses when comparing keys and when rebalancing the tree. And that makes sense, because we are chasing pointers. We are getting into unknown land and grabbing memory from God knows where into the cache. So this is expensive. So still, if we compare this with the array with binary search, we see that the array is very much faster up until around 100-ish elements. And remember that the linear search one was even faster. So here we see a payoff when we are at, say, 500 elements or more thereabouts. This is worth keeping in mind. So, can we get log n, look up an insertion without chasing pointers? Because that would be cool. Nodding, a lot of nodding, yes we can. Enter the heap. This is one of my absolute favorite data structures if you're not familiar with it. The heap is like this. It's a tree. It's a perfectly balanced, partially sorted tree. And by partially sorted, I mean that every node is sorted after or the same as its parent. And there is no relation at all between siblings, none. And we have at most one node that has only one child, and in that case, that child is the last node. And operations on it are like this. If I want to do an insertion, what I do is I create space for a new element, and then I trickle down into that space the parent if it is greater than the value I want to insert. And when I no longer have anything to trickle down, then I can insert into that space. So if I want to insert 7 here, I create a space, I see that 10 is greater than 7, so let's move it down. And then we have a new space. 8 is greater than 7, so let's move it down. And then we see that 3 is not greater than 7, so we can move our 7 in there. Then now we have an insertion. So this is cool. And to pop the top, we just remove the top, trickle up the child that has a lesser value of the siblings. And when we're done with that, we insert the last entry into the new hole. So remove this one. 5 is the lesser one, so we trickle it up. 6 is the lesser one, so we trickle it up. 9 is the lesser one, so we trickle it up. And now we take the last one, number 10. In this case, 10 is larger than 9, so we can just move it into place right away. If it was not larger, then we would trickle upwards again with that. And the cool thing with this is if we number the nodes, so we have 1 at the root, its children are 2 and 3, and 2's children are 4 and 5. We can see that the index of a parent of a node is the index of a node divided by 2, rounded down. So the rightmost one, and that has 14, node number 7, its parent is 3, because 7 divided by 2 rounded down is 3. So we can just change how we view this tree and say that it's a contiguous array. And what we're doing is just array indexing, which means that we never have to read a pointer, which may be a cache miss, see where that leads to, and follow it to some random place in memory. We know that it's a confined space, and we can do just arithmetics to figure out where to go. But the heap is not searchable, so how do we handle cancellation? So one way to do it is to split the data structure. So we say I have one struct for a timer action, and I have an action store that I store these in. And then we have the heap with the timeouts that just have the deadline and an index into the actions. An extra bonus for this is that now each element in the heap is just 8 bytes, sorry. Which means that the amount of memory that I have to fiddle with when inserting and popping is reduced, because I don't have to touch the actions very often. To cancel, I can just set the callback to null. This has a cost, meaning that cancel doesn't shrink the used memory. But on the other hand, since this is a logarithmic structure now, having twice as many entries is just one more level in the tree. So unless you're extremely pressed for memory, this is way better. So we can have our timer data here, and it turns out that priority queue that exists in the standard library is a heap as a container adapter. So I'm using the priority queue with a vector of timer data. And then schedule timer just becomes a matter of pushing something into the action store and then pushing into the heap the deadline and the index I got from the action store. Shoot first becomes more difficult because the top element may be canceled. So I have to loop through just popping elements as long as the callback pointer is null. Popping them off, they're of no value. And then either we're completely done or there is something to call in the lower half of this function. So we're doing more work here. So let's have a look. So we have our priority queue. Let's skip the action store, it's not interesting. Schedule timer and cancel timer and shoot first. Note that I'm using 1,000 here again. I'm not cheating going back, so that we can do a fair comparison with map. So get the numbers for map first and heap. All right, nice. Cycles are down, instructions are down, cache loads are down, cache misses are down, branches are down, branch misses are down. Yay, this is cool. This is cool. For the sake of completeness, let's analyze it. Adjust heap, schedule timer, push heap, shoot first. Let's see, adjust heap, that is the largest culprit. Reading standard library code again, wonderful. What's happening here? What's happening here? Get second child, so yeah, you recognize this, index multiplied by 2 plus 1 to get the right child. And do comparisons to see, find the hole, move into a hole. Yeah, so this must be. Can we see that? It's for. Yeah, it must be for. Where did I go? So moving the elements through the heap to find the right spot where we want to be. So this is going down from the root, like so. Okay. So I don't know if how interesting is this one. Shoot first. Yeah, okay. This is the action store, but we're only touching that once per insertion and once per canceling and once per shooting. We're also seeing that the random number generator is beginning to be visible. That is interesting. Yeah. So this is actually not bad. This is actually not bad at all. So, I mean, a lot fewer everything. That is great. Yeah, I said twice as fast. It was actually 4 times, sorry. So let's compare this to map. We can see that for the low number of entries, it's just blazingly fast. It's sort of equal-ish in the middle. And then it starts to gain again for high numbers. So that is interesting. But there are still many cache misses in the adjust heap functions. And I was wondering, can we do better? Can we do better? I mean, you don't have to. This is me being obsessive. This is not necessary, but why not? So how do the entries fit in a cache? Because the heap is just one contiguous vector. So the cache lines are laid out like this if we assume that the root starts perfectly on one cache entry. So when we go through this one, we see that except for the root, we have one cache line per generation. Is that actually good? I thought we should be able to do better. We really should do better. So I thought, can we do like this? We can have a heap of small mini heaps, where every mini heap fits in one cache line. It turned out I'm not the first one who have thought about this, because this has a name. It's called a B heap. But that it has a name is good, because it means that it was not a complete failure when someone discovered it. So, yay for that. So when we go through here, we see that we get 3 generations per cache line. That must be good. That must be good. So I can look at my mini heaps like so, and 7 is a really bad length to work with. But I decided to just sacrifice the first entry and say, I don't care. I'm wasting memory. I have a sacrificial node for every mini heap. But this means I don't have to do +1, -1 changes all the time, because I'm using, in the mini heap, I'm using node numbers 1 through 7. So I just multiply by 2 or divide by 2. And the next mini heap and the next mini heap. And then I have a tree with a log 8 structure. It's an absolutely insane fan out in terms of cache lines. But the code is pretty horrible. I'm the first to admit. It actually took a very long time to get this to work. So I don't know why I decided to call the mini heaps blocks in the code. That doesn't make sense, but whatever, I did. But we can see where in the mini heap are we by just looking at the last 3 bits on the index. And find the block base is the reverse, mask off the last 3 bits. And to ask, am I at the root of a mini heap, I just check, is the block offset 1, then I'm at the root. Or if, in this case, if the third bit 2, is set, then I'm in one of the leaves. So I can then say, so get me the left child of a node. Just see if it's not a leaf, then it's simple. Then I just add the block offset to move in the mini heap, and otherwise I have to do this horrible log 8 thing. And likewise for getting to the parent, it's if I'm not at block root, then it's simple. I just move up a little bit. But otherwise, again, the log 8 thing, which is not great. And also, here it's really important to be aligned with the cache lines. So each entry that I'm using in this story is just 8 bytes, and its alignment is 4 bytes. And I want to ensure that I start on the right numbers. So I need to use my vector with an aligned allocator that says, no, you must align on 64 bytes. And this is actually quite simple to write. So we get the alignment as the template parameter. And C++17 gave us aligned operator new and delete. And this is actually all that's required here to get an aligned allocator. So we can have a look at this code, see how it performs. So B heap with the align allocator. this store the horrible functions. Push is not very simple compared to a normal heap push. And pop is really, really not simple compared to a heap pop. But the rest should be familiar. That is the same. So where did we get here? Let's try it. Any guesses? Good, bad? I see a few thumbs up. Damn. Actually, this depends. It depends on the CPU. It depends on the compiler flags. But for these, it's worse. But what we can see is, yeah, instructions are up. Cache misses are down. Definitely are down. I don't know why branches are so much worse. So, yeah, this is a bit of a disappointment. But as I said, this does depend. If I'm doing O3, they are evenly matched on this machine. On an Intel machine, it's way faster with O3. So it depends a little bit. But this leads to another thing, because now the question is, remember that this is a timer. Is this better or worse, even though it's slower in this measurement? It can be better. I'm arguing that it is. And the reason I'm arguing that it is, yeah, we can compare you see the numbers they're reasonably the same, but it depends a little bit on the flags. The reason I'm arguing that it actually is better is because it is a timer in a system. In other situations, it would not be better necessarily. But the reason it is better as a timer is, if you think about how a system works, it does something, it schedules a timer, it does something, it schedules a timer, it does something, it cancels a timer, and it cancels another timer, and it does something, it fires a timer, it does something. And by touching fewer cache lines, we are evicting less data from hot cache for the rest of the system, which means that the whole system performs better, even though I've sacrificed a little bit of performance for the timer itself. So this depends on your use case. If this was instead something that you were doing for a very long time in a tight loop, and whatever otherwise happened in the system had no significance whatsoever, then this would have been a total loss. It would have been bad. So that is also worth thinking about. If we compare this with the linear array that we started with, we can see that for large number of elements, it's really good. But linear search in a contiguous space is really good, as long as your data set is reasonably small. So in this case, the break-even point seems to be at around 200 elements, roughly. And that is actually my experience, generally speaking, that it seems like fewer than 200 elements, just linear search, don't be fancy, unless profiling shows differently. More than 1,000 elements, you probably need to think about that. And in the range between 200 and 1,000, it's a hard call. So some rules of thumb. Following pointer is a cache miss unless you have information to the contrary. A smaller working set is better. So splitting the data structure gives you, like I did for the heap examples, gives you better performance. I could have done that with the linear array, and that would to have just the timeout times as one small structure and another structure for the action. That way, the amount of data to do mem move would be smaller, so it would be faster. I don't know how much faster because I haven't measured, but I would expect it to be somewhat faster. Use as much of a cache entry as you can. I have a war story. We had a prototype board for doing telecom things, a PCI board. And I don't know if you know this, but the telecom world has a beat. It goes at 8,000 hertz. And this prototype board had an interrupt for every frame. So let's say we have one frame every 125 microseconds. And on this interrupt, it scanned through an array, a linear array, to see where is there work to do, is there work to do, is there work to do, is there work to do. That was 1 bit. And the entire struct that it was looking into was exactly 1 cache line in size. So we wasted 1 cache line to look at 1 bit, wasted another cache line to look at 1 bit, wasted another cache line to look at 1 bit. When that vector grew large enough that wasting all these cache misses, we actually blew the entire cache 8,000 times per second. The system was not particularly fast. In fact, we dropped interrupts, so it failed to function. So the solution to that was to have a separate structure with just this bit. So you read a large number, check are there set bits in here, yeah, and then go to this other vector to see when there is work to do. So use as much of a cache entry as you can. Don't evict a cache entry to read a whole new one to look at 1 bit. That is not good. Sequential memory access can be really, really, really fast because the CPU does prefetching. It sees your access patterns. You start reading this memory address and this memory address and this memory address, and the CPU says, I bet you're going to read that one too. So I'd start preparing for it right away. And you're probably going to read these others also. So you get really fast accesses, and that is why this linear array is so fast as long as the data set is somewhat small. But as I mentioned also, fewer evicted cache lines means more data in hot cache for the rest of the program, depending on what your program is and what this structure is that you're massaging the cache with. This may be super important, or it may be not important at all. It depends. You have to know your system. And mispredicted branches can evict cache entries if you have an older CPU, and you can get extremely hard to understand results from cache profiling if you do. So if you're doing this kind of performance analysis on a CPU that is a few years old, be prepared. And yeah, linear access in contiguous memory just absolutely rules for small data sets. There's no doubt about that at all. And measure. Because your intuition is wrong. We have already showed that today in this presentation. So when you think about these things, when you write code, then you do what I call writing cache-friendly code. So that answers the title of the talk. What do I mean by cache-friendly? That is taking these things into account when you write your code. Some things worth looking into. To take a photo of that. Ulrich Drepper's paper is a little bit old. It's definitely not what every programmer should know about memory, because it starts with how a transistor is made. You don't need to know that. Millian Wolf had it's a few years old now, this presentation, but Linux Perfect for Qt developers. It's an introduction to how Qt works. It's well worth looking at. A disadvantage with Perf, apart from the absolutely horrendous user interface, is the number of counters you have. Yeah, I should have showed that. You have on this particular machine these to choose between. So choose carefully so that you get the information that is of value for you. Yeah, only that. Travis Downs cache counters ran. That was when I posted on Twitter this result when I have more than 100% cache miss, and I said, what? And he wrote that as a response, which it's a really good read. So read through it. And a couple of years ago, Emery Berger had a presentation at the Strange Loop conference named Performance Matters. It's an amazingly good presentation. Do watch it. And that is all I had. Thank you very much, and please ask questions.